Well, welcome you all to the next video lecture of Dr. S.J.Sarkar in Basics of Electrical Engineering. So I would be discussing the basics of an experiment which is performed for finding out different parameters of an alternator, which is there are three parameters actually: Re, that is the effective resistance of the alternator; Xs, that is the synchronous reactance of the alternator; and Zs, which is the synchronous impedance. So Xs is the synchronous reactance, Zs is the synchronous impedance. So what we can know basically that this Zs will be nothing but Re plus Jxs. So what is going to happen if you have to find out Xs? So we can find out Xs should be equal to root over Zs square minus Re square as given over here. We can say now this Xs is having two components there. One is called XL, that is the leakage reactance, and XA, that is the reactance coming from the armature flux, armature reaction actually. So the theory is actually discussed in the class, so you are aware of that. So what happened? We are going to find out all these parameters for a given alternator in the laboratory. We are in the laboratory and we have to find out the parameters. So let's try to understand how we are going to find out. The first one is determination of Re. We have to find out the effective resistance of the alternator. So what we can do, we may directly go for a voltmeter method, or we can have a Wheatstone bridge method to find out the DC resistance of the winding. So this is an alternator. We would be open circuiting the field here, and of the three terminals, from the two terminal we are connecting it to the source. We are giving a DC voltage, and then we would be measuring voltage and current. So voltage by current will be giving the impedance. Now there is some value of RH which is given over there. That RH is the rheostat. So basically the objective of this rheostat is to limit the current that would be passing through the armature winding, so that it is not exceeding the rated value. That is the only purpose. So now when the switch is closed, so what is going to happen? A finite amount of current is actually passing through it. So what we would be doing? We would be measuring what is the voltage across these 2 points. So let V be the voltage and I be the current reading. So what is going to happen? That the DC resistance of this path will be V by I. Now this part you could see that comprises of two armature conductor. So if one is having the resistance of RDC, so what we can say, this part will be having the resistance of 2 RDC, that should be equal to V by I. So therefore the DC resistance we can find out, that would be equal to half V by I. So I am talking about DC resistance. Mind it. Why? Because what actually happened that in case of AC there is something called skin effect which comes into play, and therefore the AC resistance will be different in compared to that of DC. So in the lab, generally what we used to do, we used to multiply the DC resistance with a value that is called 1.6, something like 1.6 we are going to multiply it to get the effective resistance. That is the in general method we used to do. Whatever DC resistance we are getting, we will be multiplying it by 1.6 to get the effective resistance. Now one more point, instead of this voltmeter ammeter method, directly we can connect a multimeter across it as well. So whatever reading it would be coming, that would be, we'll be dividing it by 2 to get the value of DC resistance. So this is about the determination of this effective resistance. So we can find out this Re. Now we have to find out the synchronous impedance Zs by using two testing actually. That one is called open circuit test and another is called short circuit test. So how we are going to do it? This is the setup for open circuit test. We would be doing what? We would be driving the machine at the rated speed. Rated speed will be the synchronous speed. Now, we would be open circuiting the armature sections and simply connect a voltmeter across it to measure what is the voltage. So by the way, which type of voltage it will be? It will be between the line. So it's a line voltage and it's a star connection. You could see it's a common point connected over there. It's a star connection. So the phase voltage will be the voltmeter reading divided by √3 will be the phase voltage reading. So what we are going to do? We are having a rheostat, we are having a DC supply connected to the field now. We would be varying this rheostat and noting out the value of this voltmeter. And we would be plotting it in a table. So we are having field current, we are having the phase voltage. I would be measuring in phase voltage, not line voltage. So whatever value we would be getting, we would be dividing it by √3 to get the phase voltage. So we would be putting it in the table. Now, once we are getting the value, something more than the rated value, and we could see that the value of V is not varying significantly with the variation of I, if we were observing so, means what we can see that V became more or less flattened in nature. So we would be stopping at that particular point. We would not be moving further. If the V is not varying to quite a large value, even if there is some variation of the field current, we would be stopping at that particular point. So, but that point would be above the rated voltage. We have to stop above the rated voltage only, not before that. So, once we are doing so, and then we are going to do what? We are going to plot a graph. So, how the graph is going to look like? Just see. So, this upper graph, that is OCC, this is the graph what it should be drawn between the no load voltage per phase, E0 per phase, versus the field current. So the data what we had obtained, so from that the graph what we would be getting, that would be something like this one. We are calling it open circuit characteristics because this characteristics is obtained by open circuiting the alternator. So that is the significance of this OCC. It will be drawn between no load voltage per phase and field current. Then we will be performing the short circuit test. We had performed a short circuit test of a transformer as well. So what we know, we will be short circuiting the output. So what we are going to do, we will be short circuiting the armature output, and in one phase actually we will be connecting an ammeter to measure the armature current. Now again, we have to do the experiment very carefully because a little variation of the field current can result in a significant change in the armature current. So what we would be doing, we would be carefully changing the rheostat value from 0 to some value such that this armature current is not exceeding more than 1.5 to 2 times of the rated current. So if the rated current is 5 ampere, we have to stop this experiment by 1.5 into 5, that is 7.5 to 10 ampere. We have to stop the experiment. We would not be going beyond that because that would be damaging the machine. Now we would be noting the readings. What are the different value of short circuit current corresponding to different field current. So you would be getting a linear relationship. Now the top graph of OCC, what we could see here, initially it was linear, then it keep on flattening. So if you could recall, that would be similar to that of a DC machine. And why it is happening? Due to the saturation of magnetic core. This flattening is going to happen. But SCC is operating as a much lower flux, so there is no saturation, so it would be a linear one. So we would be drawing the curve between the short circuit current and IF to get this SCC. This SCC stands for short circuit characteristic. The characteristic what we are getting on short circuiting the armature. So we are getting OCC and SCC. Now once we are getting this sort of graph, from that we can find out ZS. How? Let us suppose OA be the field current for which we are getting the rated voltage in the OCC. So if AC is the rated phase voltage of the machine, which is corresponding to OA, we would be measuring what is the AB from the short circuit characteristic. If even the short circuit current cannot reach at this point, even we can actually extend it, because it's a straight line, so we may extend it to that level to get this length AB. So OAC, that is the voltage, no load voltage, AB, that is the current. So impedance will be AC divided by AB. That would be the synchronous impedance of the alternator. So we can find out ZS like that way. Now once ZS is known, we had already found this RE, effective resistance, we can compute the value of XS. So this is the way actually we are going to find out the OCC or SCC of a particular alternator, from which we will be finding out the value of ZS and XS of that particular machine under no load condition. Now why I am maintaining this under no load condition? Because if you will be changing the load, then what may happen that XS may going to vary. The synchronous reactance is actually going to vary. So for simplification purpose, we would be taking this value of XS and we would be performing the calculation based on that. So this is what is basically the open circuit test and short circuit test of a transformer, and that is why the way basically we would be finding out the parameters: effective resistance of the armature, synchronous reactance of the machine, and synchronous impedance of the machine. So I am stopping here. If anyone have any questions, you can ask me without any hesitation. Thank you. Have a nice day.